All right, it's that moment we've all been waiting for. Yes, it's at long last the favorite chapter of every math student ever, exponential and logarithmic functions. Woo! Yes, today, unfortunately, it's only exponential functions, but logarithms are coming soon. So, of course, you're going, well, I remember what an exponential function is. We've worked with many exponents all year long, so of course, the big difference is what makes something an exponential function. And you may, of course, remember that exponential functions change where the variable is located. Now we have a base number that is a constant, and our exponent becomes a variable. That's the big difference when you create an exponential function. Exponential functions can look something like y equals 4 to the 2x plus 3 power. It can be 1/3 to the 5x power. Many, many different possibilities can happen here. However, there are some restrictions. The base has to be a positive number. The base cannot be negative. The base also can't be 0. And if you think about it, it makes sense. Because if you have 0 to the x power, what's going to happen when you take it to any power? 0 to the first power is 0, 0 to the second power is 0, 0 to the third power is 0. You don't get anything. And if you think about it, there's another number we can't have as well because it does the same thing. It just stays on the same number. And that would, of course, be the base can't be 1 because 1 to any power keeps giving you a 1. However, then a lot of people will say, well, why didn't you just say the base is greater than 1? Well, the big difference is the base can be fraction values between 0 and 1. So we can have 1/2, 2/3, 0.75. So any fractions in decimal between 0 and 1 are still possible. Now, when you think about this, if that base is always a positive number, even if I make the base some hideous decimal and I take it to the x power, what's going to happen with y every time I do that? If I take a positive number to a power, positive number squared, a positive number cubed, a positive number to the 5th power, even if I take a positive number to a negative power. Remember, negative powers simply mean dropping something to the bottom and making it positive. So even if I give you something like that, it's still going to become a positive number. So we know from this that then it is always equal to a positive number as well. So consequently then, y also must always be a positive number. And it can't equal 0 either. X, the domain, I'll point this out, x can be any real number. So therefore, the domain here, the x-coordinates you can use are anything from negative infinity to positive infinity. The range, however, that's the y-coordinates, is always going to be 0 and bigger. So those are two key factors to keep in mind. Those are going to have a huge impact when we do logarithms and do the inverse of an exponential function here next time. Now, before we get hot and heavy into our exponential functions, though, I need to do a quick review with you about exponents in general. It's been a while, and I need to make sure everybody's on the right page here with us because it does make a huge difference. So, for example, I need you in this particular section to be able to look at 3 to the negative 2 and say, hey, 3 to the negative 2, negative exponents mean switch from top to bottom. That's really 1 over 3 squared, or 1/9. And vice versa, I also need to be able to give you something like 1 over 5 to the negative 3 and have you go, oh, well, hey, that's a negative power on the bottom. I can bring it to the top and make it a positive power. So therefore, that's the same thing as 125. We also need to do a review of fractions. and I should say rational exponents, exponents that are fractions. What did 36 to the 1/2 power mean? We used it a little bit last chapter. We know that that is 36 and a root. Anytime you have a fraction exponent, it's a root. The numerator goes on the inside. The denominator is the index on the root. And so in this case, if you see a 1/2 power, that's nothing more than a square root. So we get an answer of 6. Okay, let's try a couple for good measure, just to make sure we've got this. Suppose I said, figure out for me what's 125 to the 2/3 power. You would go, well, hey, no problem. That's 125 in a cube root squared. Now, do you really want to square 125? That would be a big number. No. When you're working in these kind of problems, you always want to do the root first. So what's the cube root of 125? It's 5. And then we square it, so we get a nice answer of 25. Much easier to deal with. Okay. On the same token, one last one. What if I combine the two of them together and I give you 16 to the negative 3/4 power? What should you deal with first, the negative power or the fraction? Well, actually, I would do them both at once. The negative power, you will instantly drop to the bottom. But since it's a fraction, I'll put it in a root while I'm dropping it. Okay, is it a cube root or a 4th root? Hopefully you're out there screaming, it's a 4th root. The denominator goes on the outside. The 3rd power goes on the inside. You don't need the negative. You've already dropped it to the bottom. So what is the 4th root of 16? That would be 2 when you cube it. And, of course, you have 1/8. Okay. You have some practice problems today that go back to the review chapter at the beginning of the book, just a few to get your brain back in gear on working with these exponents, because it's going to be really crucial to us here shortly, and in fact throughout this chapter. However, before we get into solving equations and using that particular thing, we need to remember what do the graphs of exponential functions look like, because that's probably what makes exponential functions the most valuable, is what happens to exponential functions when we graph them. They have a very distinctive graph. We pretty much always know what they're going to look like. So if I said to you, let's graph the good old most basic exponential function there is for us, that would be 2 to the x. We don't want to graph fractions and decimals, so 2 would be the smallest base number we can use. And I'm going to do it this first time with your good old basic t-table. And so if I do 0, 1, 2, 3, and I plot, then that means I'm doing 2 to the 0, 2 to the first, 2 to the second, 2 to the third, because I'm subbing each of the x coordinates in for x here. What happens? What numbers do I get? Well, 2 to the 0 is 1, 2 to the first is 2, then 4, then 8. So that's all nice. Let's go ahead and plot that far. We got 0 over 1 up, 1 over 2 up. Then notice it's doubling. 4 up, 8 up. The next one would be 16, which we aren't going to do. So we can tell that this thing is going to rise very quickly. The question is, what happens on the negative side? So let's do a few negative powers. And here we go, 2 to the negative 1. What do you do with a negative power? You drop it to the bottom, and that's really 1/2. 2 to the negative 2, drop it to the bottom, that's really 2 squared, or 1/4. 2 to the negative 3, drop it, would be 1 over 2 cubed, or 1/8. So you'll notice I'm getting very small fractions, and attempting to plot these is going to become very difficult. 1/2, maybe I can get a 1/4, seriously, 1/8, probably not getting too close there. But you can see it's getting closer and closer to the x-axis. And that may lead you to remember that, oh yes, on exponential functions, the x-axis is an asymptote. So I'm putting an asymptote across the x-axis, and then I know that my curve must rise very quickly to the right, but follow the asymptote to the left. We call that exponential growth because it's growing very quickly. Now, You might also remember back in the good old days, we talked about exponential decay as well. And that is when we made our graph fall. And so how did we make our graph come downward? Well, I would like this exact graph we just drew to come downward, so I'd like it to go 0, 1, I'm going to go 2, 4, 8, etc. I want it to come down now, though, so I'm going to still have an asymptote on the x-axis, and I want it to come down and then follow the asymptote. So I'm coming down here, zoom, following out that way. That's exponential decay, but what do I have to do to the equation to make that happen? Well, there's actually two ways you can make that happen. Hopefully you're going, but well, you just flipped it over the y-axis. How does one flip a graph over the y-axis? Well, you know it's a negative sign. It's a matter of which place is it. Which one's the right one? Is it when we throw a negative out in front? Or is it when we throw a negative on the x? Which one makes us flip over the y-axis? Well, hopefully you're thinking of something simple like parabolas. We know the negative in front on a parabola made a parabola go upside down. So it can't be that one. And yes, it is when you have a negative exponent. When you have a negative on the x, it makes you flip over the y-axis and get exponential decay. But because that's a negative exponent, that also means, since it's a negative, I could drop it to the bottom as 1/2. And so it's also in the land of exponential functions. It's when you have a base that's between 0 and 1. You have a base value, whether it's a fraction or a decimal, between 0 and 1. You also get exponential decay. So those two create this exact same graph. It's just a matter of how you want to look at it. Do you want to make the base a fraction, or do you want to make it have a negative exponent? Now, I will comment, since we're here talking about flipping, I want to get the other one on there. If you want to flip over the x-axis, not flop, if you want to flip over the x-axis, it's just like every other graph we have flipped upside down. Yes, you put the negative in front. Now that creates an interesting graph. If you flip it over the x-axis, then you're going to have it at 0, 1 on the going downward. It's going to go falling off in that general direction. It's still going to follow the asymptote on the left, but it's going to turn upside down. So remember, let me put the original exponential function is rising, so if you flip over the x-axis, it's now falling off to the right. So you are going to have to be careful when graphing and watch those flips. Sometimes you'll even get a double flip. So let us go try graphing a couple, and remembering, of course, how our graphs shift around as well. So let's create a couple functions here we're going to graph. And in particular, I want to do something like this. I'm going to give you 2 times 3 to the x plus 2 power minus 9. Okay, you know what all these additional numbers I've added to it do to the graph, because it's the same as every other graph we've ever drawn. So we know the negative 9 in the back is going to send us down 9. That's not a bad thing on an exponential function since they grow so fast. The x plus 2 is, yes, sending us left 2. Our base number is 3. That'll be important when we do our t-table here momentarily. And then what does the 2 in front do? That's still our stretching factor. And what did you do with a 2 in front of a parabola or any other graph we've drawn? You multiplied it by the y-coordinates. So we're going to do the same thing here. as we plot this one. So let's, however, get this one moved over and shifted. It went left 2, down 9. Okay, the key thing to remember on an exponential function, the graph does not pass through that origin whatsoever. The only thing that passes through the origin is our friend the asymptote. Okay, so our asymptote would be sitting there. Now, we actually have to plot our points. So, since our base is 3, you're just plotting 3 to the x in order to graph this. 0, 1, 2, doubt I'm even going to do 3 here because that's going to get too big. But if I do 3 to the 0, I'll get 1. 3 to the first is 3. 3 to the second is 9. And, yep, 3 to the third is 27. Probably not doing that one. Too big. Okay, but am I done with these coordinates? And the answer would be no, I'm not. I still, since I had a stretching factor of 2, I would have to double each of these coordinates and take it times 2, each one of those times 2, so I would be going to 2, 6, and 18 now. So if I plot this from the origin, normally I'm at 0, 1, this would put me at 0, 2. Then I would be 1 over and 6 up. And then by the time I'm 2 over, I am 18 up, which would put me clear up there. So this is a definite example of pretty steep exponential growth. And it's rising very quickly. Kind of missed that one point there, but okay, we get the gist of the idea. So that would be a basic graph of an exponential function. Now, the only other thing I need to show you is something that those of you who've had pre-calc have done before. If you've only had algebra 2, you didn't get the pleasure of graphing this most hallowed number of mathematics. Yes, we also have to learn how does one graph an exponential function with our good friend base E. So if I was to give you, we'll put a little pizzazz in it. Say, let's graph e to the, let's do 5 minus x plus 1. All right, if I was to ask you to graph that function, you would, of course, still figure out the shift first. And you would look at this and go, well, it's going up 1. But what do I do about 5 minus x? You cannot determine a shift if the x is negative, so you'll hopefully recall we usually, shouldn't have drawn that line there, sorry. Let's try that again. Get that a little higher here. When we want to deal with this, if we have a 5 minus x, we prefer to pull the negative out of it and make it x minus 5. So that way we reverse it, and now we can tell that, oh, I really need to go right 5. So I'm going to go right 5, up 1 here. And I'm immediately still going to put my asymptote through that point, or through the origin there. Okay, and then when I go to make my t-table, I am thinking, oh, well, it's base E, so I have to do the powers of E, which, okay, for your first time, you don't know them, but you soon will. Okay, you already know a couple of these. E to the 0 is 1. You will hopefully remember, or you can go to your calculator, the number E itself has an approximate value of 2.718. We are just going to live with 2.7 when it comes to graphing. So you're going to plot 2.7. If you go to your calculator and hit e squared, you'll discover, rounded off, e squared is approximately 7.4. I'm going to settle for you plotting those 3 points anytime you need to graph e. Not anything super fancy. Now, is this e flipped anywhere? We had a negative sign. Is that the negative that causes us to flip over the y-axis and decay? Or is that the negative that causes us to flip upside down? Well, hopefully you're screaming that's decay, that's a y-axis flip. So, yes, this is going to be exponential decay, we're coming down. So when it says plot 0, 1, I'm still above the origin. When it says 1 over 2.7, I have to go left 1 over 2.7 up, and then 2 over 7.4 up. And that's close enough to get an approximate graph of our exponential function with base e. So e is no different. You do need to stick 2.7 and 7.4 in your head for future use. Okay, I'm going to stop the video there. That's a good place. We're done with the graphing, and then make a separate piece.